All right, so we were talking about posets, Mobius functions, and I finished last time by proving this theorem due to Philip Hall. I lied in class. I said Pauli, it was a different Hall from the Hall marriage theorem, but it turns out that it's the same Hall. It says this. So if you have any finite poset and you add a bottom and a top element, and if you let Ci be the number of chains from 0 to 1 of length I, then the Mobius function of the poset from the bottom to the top is equal to C0 minus the number of 1 chains plus the number of 2 chains minus the 3 chains and so on. Okay. So this was this kind of strange formula for the Mobius function, but at least it told us that you can compute the Mobius function if you know how to count chains of the various sizes in the poset. Okay. Now, I told you a little bit about how, I just mentioned that this had a topological significance, and so that's what I'm going to explain to you next. Okay. So we want to give a topological meaning to this, and so let's do the following thing. I'm budgeting my board here. So okay, just go over here. So a simplicial complex, sometimes people will call this an abstract simplicial complex. Delta on, let's say, a set S is the following thing. It's a collection of subsets of S such that for any element of the set, the singleton is an element of the simplicial complex. Okay. And if you have something in the set, something in the complex and a subset of it, then G is also in the simplicial complex. I think this is most usefully explained in an example. So let's say that V is the set of 4 elements. Okay. What can delta be? Well, let's say that it contains the empty set, the singletons, the pairs AB, AC, BC, and E. Okay, so here I'm being lazy and I'm not putting brackets around each set, but this is actually a collection of sets. Okay, it's not just laziness. If you put brackets, it's impossible to read. Okay, so the first thing you should check is that every one of these things is in your simplicial complex, and that's true. Okay, and the other thing is that whenever you take something in the simplicial complex and you look at subsets of it, it's also in the simplicial complex. So if BD is in the simplicial complex, then its subsets are also part of the list. Okay. Now, this is a combinatorial definition, but actually it's often more useful to draw a picture. And when we think of a simplicial complex, you should usually just think of this picture, where you have a node for every element of the set. Okay, and whenever you have a subset in delta, you draw a corresponding simplex here. Okay, so for example, if you have AB here, then you draw the simplex with vertices A and B, which is a line. Okay? From A to C, this one. From B to C is this one. From B to D is this one. Okay? And if I draw it like this, and I think of this as actually a geometric object or a topological object, then I can forget of abstract, and then this would be my simplicial complex. Okay? And so, actually, it's usually a more, well, sometimes for combinatorics this is a useful definition, but really it's often more useful to think of this as you have a bunch of simplices. Okay, so what's a simplex? It's either a point, or a segment, or a triangle, or a tetrahedron, or the higher dimensional analogs of these things, and you kind of put a bunch of simplices and you glue them along faces if you want. Okay, so another simplicial complex is to put a full triangle. And then maybe you glue a hollow triangle here. Okay, so this segment and this segment, and then if you want, you can put a tetrahedron in here. Okay, and then maybe you glue another triangle here. You glue a segment here, and maybe you want to go around. Maybe you glue a triangle here, and you glue a segment there, and so on. Okay. And so you just have a collection of simplices with the property that whenever two simplices meet, they meet on a common face. And it's easy to see that this kind of geometric picture is equivalent to this combinatorial picture, and it's useful to go back and forth. Okay? All right. So here I didn't fill in this triangle. This is an empty triangle, and the reason is that the set ABC is not here. Okay? But if the set ABC was part of my simplicial complex, then I would fill in that triangle. And you see this property says that if I have a triangle, then every face of it is also in my simplicial complex. And so actually it's usually instead of calling these subsets, we call them faces. Question?
Why is it called a simplicial complex if we can take subsets of, I mean, I don't understand what simplicial means in this context.
So the question is why call this a simplicial complex, and I think from this definition it's very unclear, and so this is a better way of thinking about it. So let me repeat again a little bit more clearly what I was trying to say. Here's a simplex, right? This is a two-dimensional simplex, and so if I want this guy to be in my simplicial complex, I would actually have the set ABC. That would be part of my simplicial complex. But if I want ABC, then I also have to have all its subsets.
Mm-hmm.
Right? And the way of thinking of that is that I have to have this edge as part of the simplicial complex, this one, the vertices, etc. So if I have ABC, then I'm forced to put the pairs and the singletons and the empty set. Okay. And now maybe I think, okay, let me add another vertex. Well, if I add that vertex to my geometric picture, then I have to put it in my simplicial complex because all singletons are in the simplicial complex. And then maybe I say, let me add this segment. Then I just throw in CD into my simplicial complex. Okay? And its subsets are already there, and so I don't have to do anything else. And so you just kind of build it like that, and so it's just a complex made out of simplices. That's why it's called.
But does this definition allow for A, B, C, D to be an element? Because that's a subset of S.
Yeah, so it could be that the full set is a simplex is a face of the complex. And if the full set is a face, then every subset is a set. And that's an example of a simplicial complex. So
Okay. So if we
let Fi be the number of I-dimensional faces of my simplicial complex. Okay, now when I say I-dimensional, I'm thinking in the geometric realization, and so if I want I dimensions, I need I plus 1 vertices. So faces, so I-dimensional means size I plus 1. So if I'm thinking geometrically, I can think in dimensions. If I'm thinking combinatorially, then I know that to get a triangle, I need 3 vertices. So 2 plus 1. And let's define let me first tell you the name. So this is called the Euler characteristic. Actually, I'm going to define the reduced Euler characteristic. What you do is you subtract the faces of dimension -1. That's the weirdest term, we'll talk about it. Then you add the vertices, you subtract the edges, you add the triangles, you subtract the tetrahedra, etc. Okay. What is this weird thing? Dimension -1? So that doesn't really mean anything geometrically, but it means size 0. And so here I'm just accounting for the fact that the empty set is in my simplicial complex. Okay. So this is just a, I mean, it's usually a 1, unless your simplicial complex doesn't contain, actually no, your simplicial complex cannot not contain anybody because it has to contain the singletons. Reduced is only put because of this f minus 1. So it's sometimes more common to just define it like this, and that's the usual Euler characteristic. They just differ by 1. The only difference really is how they treat the empty simplicial complex on the empty set. So don't worry about the reduced thing, that's not a big deal. Okay? Okay, so I put these next to each other so that they look similar to you, and so that I get you to think that this might be an Euler characteristic of something. Okay? And it is. So this is the Euler characteristic of delta, okay? And now let's make another definition. Okay? So if I have a poset P, like I did here, the order complex of the poset P is the simplicial complex whose faces are the chains of the poset. Okay. So an example of this. So let's say that I start with a poset like this one. Okay, that's a poset. We're going to call the elements A, B, C, D, E, F, G. Okay, this is my poset. And now I'm going to build the order complex. Okay? So in the order complex, I'm going to have first a vertex for each I have a vertex for each element of the poset. Okay. Now I did this ahead of time, which is why I'm laying them out like this. It's a bit of a trial and error thing to see what's the nicest way of drawing it. Okay? But then what do? I say, okay, first of all, what are the chains of one element? Well, the chains of one element are just the elements. Right? And so those are just the points here. So those points are in my simplicial complex. What are the chains of two elements? For example, D is less than E. That's a chain. So I put D less than E. A is less than E. A is less than B, less than C. Right? So A is less than B, A is less than C. B is less than C. D is less than C. F is less than B. A is less than G. And F is less than G. And trust me, I did do them all. Okay, I did them kind of in this order, but these are all the comparabilities. These are all the chains of size 2. What about chains of size 3? There's only one, which goes from A to B to C. Okay, and so I should put a triangle ABC. Okay, and lucky. I mean, it's not lucky, of course, but the boundary is there already, and I can fill it in. Yeah.
What about FBC?
Oh no, FBC. Yeah, you're right. Okay. Yeah, FBC, you're right. FBC is also. See, I told you it's a bit of a. Okay, so let's. So here's ABC. So I should have probably put F. Forget it. So really, a better strategy is to start with the triangles, right? Those are going to be what determines a lot of things. So let's first start with ABC, FBC. Are there any other chains that I missed? All right. So let's lay down those two triangles first. Okay, so that's good. We should put them with B, C, A, and F, and these are both full. Okay, and then what did I do? C, D, E, and A are like this. A is connected to E is connected to D, is connected to C, and then A, B, F, and G. So that looks like this. DE, DC, A is connected to E, B, C, and G. B is connected to everybody but G, D, and E. That was good. F is connected to G and B, and C, and G is connected to F and E. Do we agree? So there you go. That's the order complex. Now, what you should realize is that the number of chains of the poset of length I is equal to the number of faces in the simplicial complex of, I guess, if a chain has length I, then it has I plus 1 elements, and so it has dimension I. And so really these two things are the same as each other except for that -1 term, right? Which I'm a little bit confused about actually because I don't have that in my notes. I don't know if I said this already, but I always get confused with whether it's reduced or not reduced. But anyway, the theorem is that the Mobius number from 0 to 1 is the same thing as the Euler characteristic reduced of the order complex. And And I think what's happening actually is that I just missed a 1 in this formula. I think this formula starts with a 1. Because this theorem is true. Question?
So that is the Mobius function for p hat.
Oh yeah, sorry, this was the Mobius function for p hat.
So,
Because I'm going from 0 to 1, and those are in p hat, but not in p.
so does that matter that we don't have a 0 and a 1 element in our p over there? What's the or so that's
So-
what you would start with and then add the 0 and 1 element, you're saying.
Right, so what if we want p hat, then we add a bottom element, then we add a top element. And so what this is saying is that the Mobius function from the bottom to the top in this new poset is equal to the Euler characteristic of this one. Okay? And yeah, I'll fix it in the notes and figure out what the difference is between these two. Another difference that I'm realizing is that here I'm adding a bottom and a top element, which changes the height by 2, but that doesn't change the sign because of -1 to the anything. So there's no problem with the sign, but I'm just off by -1 somewhere. Okay. Anyway, so this is one of these moments in. Give me just a second. This is one of these moments where sometimes you think you choose a field of mathematics, and then it ends up that you didn't really get to stay in that field, because that means that if you like the combinatorics of posets, if you like Mobius functions, then it turns out you actually should be learning some topology. It's a good reason to do it because because for one thing, if you want to compute Mobius functions, it helps you if you understand how to compute Euler characteristics, and the other way around actually, that sometimes you want to compute Euler characteristics of topological spaces, and you can do it through combinatorics. Okay. So this is kind of one of the starting points of topological combinatorics, which is a whole field in its own. And if you're interested in this, let me recommend a survey called Poset Topology by Michelle Watts. I think it's called Poset Topology, Tools and Applications. Okay. All right. So let's talk a little bit about some basic properties of Euler characteristics that are going to be useful to us. So one is that the Euler characteristic of a simplicial complex is actually a topological quantity. It only depends on the geometric slash topological space, which we call the geometric realization of delta. Okay. Now, when I say that, what I mean is just that you're going to think of this as a geometric thing, not as a bunch of sets. Okay? And also, you're even going to forget the subdivision. So you're just going to think of this as a topological space. Topological space doesn't say that this thing is cut in half. Just from this topological space, you can figure out the Euler characteristic. And let me just write a formula that might or might not mean something to you. So, in fact, the Euler characteristic is usually defined differently. It's usually defined as the alternating sum of the dimensions of the homology. Okay? And so maybe you know what a homology is, maybe what a homology group is, maybe you don't. But really, I think it's pretty okay for for a lot of purposes of what we're trying to do today, you can just think of this as being like I-dimensional holes. Okay. There you go. Think of this as just holes. So for example, here, this space has two holes. And the holes are of what dimension? Well, how do you define the dimension of a hole? You kind of define it by what's surrounding it. Right? So, for example, if you have a circle, that circle is a one-dimensional thing, and the inside is a one-dimensional hole, which is different from if you have a hollow sphere. Okay, that's a hole, but it's a two-dimensional hole. Okay? So there are holes of various dimensions, and homology groups are supposed to actually quantify that. It's a little hand-wavy at the moment, and a homology group exactly tells you how to make that precise. Okay. So this thing has two holes of dimension 1 and no other holes. And so in particular, from that formula, we get that this thing has Euler characteristic what? Like I said, we only have two holes in dimension 1. Okay, so this is minus 2 for the two negative holes. Okay, so that's the topological way of computing this. Okay. And so I want to point out to you how magical this is by, taking into account the idea that actually these two things are equal to each other. But this one is topological. It talks about the holes of this thing. And this thing is combinatorial, and we have a recipe for computing it, and we know how to compute it. So let's compute this Mobius function. And if I don't make any mistakes, we should get minus 2. It's one of those moments where I'm really hoping I haven't made any mistakes, but here you go. 1, minus 1, minus 1, minus 1. Then here, these guys are below, so this here, the Mobius function is 1. Here, it's a 1. Here, it's a 1. What about here? I have the things less than it are B, D, F, A, and the bottom. So I have 3 minus 1s, 2 1s, and so this guy should be another 1. And then, total I have 5 1s, 3 minus 1s, so this is minus 2. And so there you have it. This minus 2, which is the Mobius number, is the same as this Euler characteristic, which is topological. I think this is super cool. And we proved it. We just proved it. Okay, so now, the other thing is that Euler characteristics are topological things, which means that you can do topological operations to your spaces. So this thing doesn't change when you kind of change thing. Doesn't change under some topological operations, which I'll write the name, homeomorphism or homotope equivalence. Okay, and these are big words, but this is when people talk about topology and they try to explain topology to somebody that's not a mathematician. Usually, the way they do it is that they tell you that there's the coffee mug and the donut, right? That's the classical example. The coffee pot, and the donut are homeomorphic. That's the fancy word that we don't tell people outside of our cult. But what does it mean? Homeomorphism means that you can kind of change the shapes of things continuously. So, for example, you can take are things that have sharp corners and just kind of massage them a little bit. For example, make them have round corners, have no corners. Okay, that's a homeomorphism. You're just kind of deforming the shape without breaking it. Formal definition is that the forward function is continuous and the inverse is also continuous. You do this, the Euler characteristic doesn't change. Homotopy is a little bit more powerful. You can actually even take arms and kind of push them in. And that's a homotopy equivalence. And so we could take this thing, right? And we can kind of massage it to make it look like something more familiar. For example, we can take this whole A, B, C, and F and just squeeze it into a point. And that's a homomorphism. Squeezes into a point. And then you can take this square and kind of make it round. And you can take this square and make it round. So these things have the same topology. And so then, if we know what the Euler characteristic of this is, then we know what the Euler characteristic of this is. Which, of course, brings us to figuring out what the Euler characteristic of basic things are. Okay. And so, for example, what's the Euler characteristic of a ball? That's a very fundamental topological object. The n-dimensional ball. What is this? These are it's the full ball, right? So you take a point in n dimensions, and you look at the points that are a distance less than or equal to 1 from it. Okay, so it's a solid ball. What's the Euler characteristic of that? Well, you can take a ball and squish it, and that's the same thing as a point. It has the same topology as a point. It has the same Euler characteristic as a point. A point has no holes, so this is 0. And reduced Euler characteristic. What about the sphere? This is a ball. This is a sphere. So a sphere is a hollow ball. The points that are a distance equal to 1 from a point. Okay. Well, that has one hole in dimension n. Right? So the Euler characteristic of that is -1 to the n. And then there are theorems in topology that tell us what happens to the Euler characteristic when we put two things together like this. This is -1 and this is -1. When you put them together, it's -2. And so it ends up being, for example, actually this is the most I think the most commonly used thing in combinatorics is that if you take the Euler characteristic of what is called the bouquet of spheres. Sometimes people say wedge of spheres. Sometimes they say bouquet of spheres, like a bouquet of flowers, a bouquet of spheres. So if you take a bouquet of, let's say, k these spheres, then this Euler characteristic is k times -1. Each sphere contributes 1 -1 to the d. So for example, this is a bouquet of two spheres. Okay? And so this shows you that there's really very intimate relationship between Mobius functions and Euler characteristics, and so you want to start learning how to do these things, compute the Euler characteristics of things. But also the remarkable thing is that there's this huge toolkit that was developed by Michel Wax and Anders Bjorner and other people, and it's all outlined in here, where there's several combinatorial techniques to compute these Euler characteristics without having to, you basically get to compute them in a very combinatorial way. So there's a really powerful toolkit, and very often in combinatorics, when we do these computations, we use some of this toolkit that has a lot of great toys to play with. Okay. But yeah, so I just wanted to this is the main first point that I wanted to make today, is that Mobius functions are really Euler characteristics. All right. So now, any questions about that? By the way, I should say for the rest of the class today and the rest of the next class, more than trying to prove a lot of things, I just want to show you some things that are interesting and give you an idea of why they're true.
So those, that's a bouquet of two-dimensional spheres.
This is a bouquet of two one-spheres.
One sphere.
Because the dimension of the sphere is given by what surrounds it.
Oh, right, okay.
So it's a convention. You can see why you would want to call this a two-sphere, but it's called a one-sphere. Okay. So now the thing is though, I mean this is a small poset. Yeah.
When you generated the order complex based on the poset, that is always uniquely generated based on the poset, correct?
Yeah. So given the poset, this construction is unique. I mean,
Is that uniquely constructed backwards too, given the order complex that the poset can be uniquely constructed from it?
so the question is if I mean going from here to here is unique. The question is if the other direction is unique. So if I give you the order complex, can you tell me the poset? It's a good question. I mean, certainly topologically it's not true. So, for example, I mean, if you don't know that this thing is subdivided, it could be that B and C are comparable, or it could be that A and F are comparable. Topologically, they're the same thing. Okay, so I'm pretty sure you can use that to give examples of order complexes that are. I mean, actually, I know that you can give realizations of order complexes that are the same underlying space but different combinatorics for the poset. But it's an interesting question actually that I hadn't thought about. If I give you the order complex, then you can certainly recover the graph of the poset, right? You can say what the points are. The points are the points from here, and whenever you have an edge here, you have an edge here also. Right? But can you recover the order also?
Then that's what I'm wondering. Because even if given knowing that in that order complex, that those are in fact triangles in A and F are not directly connected, would it still be unique for the poset?
It's a really good question, and I don't know the answer offhand. I think the answer is not too hard to get. It sounds like a good exercise to think about. I mean, if it's true that you can recover the poset from here, it should be easy to prove it. And if it's false, then you try to prove it and you find the counterexample along the way. But it's a good question. I'm not sure of the answer right now. I mean, okay, so let me give you a silly reason why the answer is no, is that the poset could be like this or it could be like this. And those have the same order complex. But that's cheap. So
I think if we switch the order of B and C, we would come up with the same.
you think if we switch B and C, we get the same?
Or is that also the same as just flipping
No,
No, because you would lose the face.
it? Well, I mean, F would still be connected to C, but it would go like this instead.
Yeah. It's a good question. You guys should think about it. We'll put some comments on the YouTube video to answer it. Okay. So I think that's it for this picture. And so what I want to do next is talk about a family of posets that I like a lot that we haven't discussed. So the phase lattices. This is what this picture that I drew is about. So let's say that you take a polytope. Okay. What should I say about polytopes? I mean, there's a huge theory of polytopes, and I know some of you are familiar with it, some of you probably aren't. For what I'm going to say today, if you want to think about three-dimensional polytopes, then they're what we usually call polytopes. In n dimensions, a polytope is taking some points in n dimensions and taking their convex whole. Okay, the smallest convex set that contains them. So we're going to take a polytope like this, and then we're going to let L of P is going to be the set of faces of P partially ordered by containment. Okay. So here I'm doing this for the octahedron. Okay. And I made a mistake here. It's customary to call the empty set a face of any polytope. Okay. One reason is that it gets for a nicer poset. So here's the empty set. Then here are the vertices. There are 6 of them. Here are the 12 edges. Here are the 8 faces. They're all triangles. And then here's the full polytope. Okay. You might wonder why I labeled it like I labeled it. Right? So this is lowercase a, b, and c, which are kind of diametrically opposite to capital A, capital B, capital C. And the reason that I did that is that that's a nice labeling where the faces are all the things of the form A, B, C, where you get to choose whether each letter is capital or lowercase. Any A, B, C combination is a triangle, and so there's 2 to the 3, 8. And then, okay, here's where I just have to hope that I did it right. If you see that I missed some edges or I have some extra ones, let me know. But the containment, I think I got it right. And even though the containment is defined by subsets in here, you can actually just think of it as being an order. The partial order just tells you what vertices are contained. Right? And so instead of thinking geometrically, I can just think this label is a subset of this label. And that's really how I drew it. So like A capital B is a subset of A, C capital B. So that's a poset. Okay? Now, here are some facts about it. This is a lattice, actually. Meaning that if I have 2 faces, F and G, then there should be greatest lower bound for them. Okay. And that's actually pretty easy because it's just the intersection. The intersection of 2 faces is a face with the stipulation that if the intersection is empty, then we're calling the empty set a face. So from this definition, it's clear that this is the meat of F and G. What about the join? The join of 2 faces. It's basically the smallest face that contains them. How do I know that it's unique? One way that I know that is just using this cheap trick that if you want to prove that something is a lattice, then it's enough to prove that it has a meat and that it has a minimum element. Minimum? Yeah. No, that it has a maximum element, I'm sorry. So if you have a meat and you have a maximum element, then for free you're a lattice because your join operation, the join of F and G is just going to be, we're looking for the lowest upper bound. What we're going to do is that we're going to consider all the upper bounds. Okay. And we're going to take their meat. Now, that is not empty because I have a top element. So that top element is a member of this join, and so that's a well-defined join. And it's very easy to show that this is indeed the join operation. So it's a very useful trick to show that something is a lattice. Okay. So it's a lattice. Now, maybe to go back to what we just said, what happens if I reverse the poset? So if L is the lattice of polytope, what happens if I consider L opposite? Okay, so it's the same poset, just upside down. It turns out that that's also the phase lattice of a polytope. And what do you want? You want to have this upside down. So you want the polytope where the vertices correspond to the faces of this guy, to the maximum dimensional faces, and so on. Okay. So what do I want to do? I want to imagine that I put a vertex, let's say, in the center of each one of these faces. Okay. And then, so for example, here in the front, I have 4 vertices, right, corresponding to ABC, capital A, B, C, A, B, capital C, and capital A, B, capital C. And I connect them. So like this corresponds to A, B, C. This corresponds to capital A, B, C. And I connect them here if the 2 facets intersect in codimension 1. So these 2 are connected, and therefore these 2 are connected. These 2 are connected, so these 2 are connected, like this, this. But for example, I don't connect this one and this one because this facet and this facet don't intersect in a line, they intersect in a point. Okay. So I drew the 4 in the front, but there's also 4 in the back. Okay. And if you do this carefully, you're going to see, probably you're familiar with this picture, you're going to get a cube. This is A, B, C, A, C, and so on. Okay. And this is what's called the polar polytope.
What do you say that's called?
The polar polytope. And let me just say in words how you define the polar polytope. So if you look at a polytope, there's 2 ways of describing it, which is, one is to tell you what the vertices are. This one, to tell you the vertices are these. Or the other one is to tell you what the walls are, what the facets are. And so I tell you, my polytope is less than or equal to this plane, less than or equal to this plane. Each plane is given by some linear inequality of the form, some linear form is less than or equal to 1. And so if I have a polytope and I look at the describing inequalities, so each inequality is some linear thing dot x less than or equal to 1, then those linear forms, I use them as the vertices of my polar polytope. And vice versa. And it's a fact that there's a bijection between faces here and faces here that reverses the order. So I have this. So that means that if you take a phase lattice and you turn it around, it's still a phase lattice.
Why isn't it called the dual?
So the thing is that there's something called sometimes it's called the dual also. People call it the polar polytope or the dual polytope, and those are both fine names according to what you're trying to do. Sometimes people call it polar because there's something else called dual. So it's to not confuse. Okay. Now let's talk about something else. So what happens if I look at the interval from the bottom to some element of the poset? Like this one. The element from the empty set to A, capital C, capital B. What is that? Well, these are the faces that are, that contain the empty sets, that's all of them, and are contained in A, capital C, capital B. Right? And so that's going to be precisely the phase lattice of the face A capital C capital B. So this is just the phase lattice of my face. Okay, so that means that if you go from the bottom to some point, that's also a phase lattice. What happens if you go from a face to the top? Is that a phase lattice? Well, it kind of is for the dual, right? So you know, if I'm gonna go from F to 1, then I can flip my polytope, and that's gonna be from the bottom to F polar. Okay, so this is the lattice of F polar, which is a phase of the dual polytope. Okay. So if you go from somewhere to the top, that's also a phase lattice, and therefore any interval is the phase lattice of a polytope. I want Fg to be the phase lattice of a polytope. I say, well, 0g is the lattice of phase lattice of a polytope, and within there, F top is the phase lattice of a polytope. So that means that the phase lattices of polytopes are closed undertaking intervals. And that's very useful. So why is that very useful? It's very useful because it helps us compute the Euler characteristic very easily. I mean, it helps us compute, well, the Euler characteristic or the Mobius function. So here's a theorem. If L is the phase lattice of a polytope, then the Mobius number from 0 to 1 is -1 to the dimension. So what am I saying? What I'm saying is that if you wanted to compute the the Mobius function of this poset, let's say just the Mobius function 0, comma something. You know, you start with 1, then here we always get -1s. Then here we just get 1s. Here we just get -1s, 1s. Whenever it's a phase lattice of a polytope, it's just 0, 1. Sorry, it's 1, -1, 1, -1, 1, -1. Okay. So why is that? There's a couple of explanations. Let's see, what explanation should I give you? Depends on how much time do I have to draw a picture. Maybe we have time for both explanations, okay? Just trying to figure out if I should erase this or not. Say that we. So this is the main conclusion of what we just talked about. So L is the phase lattice of a polytope, and F is less than or equal to G, then this is the phase lattice of a polytope. Let me show you one explanation. One explanation comes from here, okay? Where to compute this number, I should compute the order. I should figure out what the Euler characteristic of the order complex of this thing is. Which should sound like a very daunting task because I'm supposed to make the order complex of this thing, which already for this little post that I made a mistake. Imagine how I'm going to try to do this. I'm going to do it anyway. Just I need your help. Don't let me make mistakes. So what I'm going to do is I'm going to take my polytope. This. So this is A, C, and I'm about to draw the ordered complex of this poset. So this is L, and here I plan to draw the ordered complex of L. Sounds like I'm set up for disaster because this is even smaller than this, right? I have to fit this whole picture in here. But it's going to work out. Now, just so that this is more visible, let's erase the back of the polytope. Okay. Let's erase this stuff. Remember that it's there, but let's erase it. Okay. And now what I'm going to do is that I'm going to put a point in the middle of every face in there. So I put a point, for example, in the middle of here, 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 here. Okay? And I'm going to put one in the middle of each edge also. And I'm going to connect everything in what's called the Barycentric Subdivision. Okay. I think I'll just do it and then we'll see what happens. So, okay. And these guys all have natural names. Right? This is lowercase c, right? This is BA, this is C, capital C. So you see I'm putting a red dot. It's useful to color them. Okay, and let's color the dots in the middle of each triangle black. So I'm putting a red dot in the middle of each edge, right? And so the red dots are exactly in correspondence with this floor. And then I'm putting a black dot in the middle of each triangle, so they're in correspondence with these guys, and they also have very natural names, right? This is ABC. This is AB capital C. This is B capital A capital C, and this is BC capital A. So at least the dots in this picture correspond to the dots in this picture. I'm not drawing the ones in the back. They are there. Question?
Is there like a dot in the center for P?
Why do I not put a dot in the center of P? Because I want the Mobius function of P hat, and so I take the order complex of P, where I drop the top and the bottom element. So that's a good point, because really what I want is not delta of L. I want delta of L minus the top and bottom elements. Okay, now where are the chains? For example, if I take a chain from A to AB to AB capital C, this goes from A to AB to AB capital C. It's that way, right? And I claim that this is exactly what happens, that every single triangle that you see in this picture corresponds to the chain that I see here. Okay? And so maybe I'll draw just one more example and then I won't draw anymore because we'll get really lost. So for example, I could go from capital A to, let's say, capital A and lowercase b to, I don't know, to this one. So capital A to BA to BCA. Okay. And so the point is that this thing is the same thing as what's called a barycentric subdivision of your polytube. Okay? And now if I remember that the Euler characteristic is a topological thing, it doesn't care about subdivisions, it doesn't care about all these lines that I drew, it just cares about what's the shape of this thing, and this thing is a polytope. And a polytope, a hollow polytope, is just like a hollow ball. You just have to take away the corners. So this is the same thing as a ball. Actually, I think it might be d or d minus 1, I'm not sure, but it's in any case, it's one sphere, and so it has Euler characteristic minus 1 to the d. So this is one argument for why this theorem is true. Now, another argument is that the Euler characteristic is the alternating sum of the faces. And this is, so we said it was points minus edges plus triangles and so on. And if you are familiar with Euler's formula, that's exactly what Euler's formula says. For example, for three-dimensional polytopes, Euler's formula says that the number of vertices minus the number of edges plus the number of faces is 2. Okay? And this is just the same thing in any dimension. So really this is Euler's formula in disguise. Okay, so that's a nice explanation. And the other nice thing that I get is that if I want not from 0 to 1, but from any f to any g, well, that, you know, because fg is the phase lattice of a polytope, that's also minus 1 to the something. It's going to be minus 1 to the dimension of g minus the dimension. So the Mobius function of these phase lattices. Actually, since I'm thinking of lattices, let me just call this the height from f to g in the poset. Okay. All right. So there we have it. Yep.
Isn't that also really close to the Mobius function for the Boolean lattice? Doesn't that also go like?
That's right. So the Mobius function of the Boolean lattice is exactly like this. It's just. You have a comment or?
I was wondering if it's the Boolean lattice is coming from a cube.
So one possible explanation for why the Boolean lattice might have this is that the Boolean lattice might be the phase poset of a polytope. And it actually is. That's actually the phase poset of the simplex. Simplest phase poset. And actually, let me make a definition that a poset is Eulerian if the Mobius function is like this. For all x and y. Okay. So we're saying that the Boolean lattice is Eulerian. We're saying that the phase lattice of any polytope is Eulerian. Okay, so let's talk about some applications of this. So you see the name Eulerian comes from the fact that it's coming from Euler characteristics. examples. Boolean lattice or the phase lattice. Now let P be a simplicial polytope. So what does that mean? Every proper phase is a simplex. So here we have an example where the polytope is not a simplex, but every face of it is a simplex, right? The facets are triangles, and everything below is simplex. Okay. Let Fi be the number of I-dimensional faces. Okay. And so Euler's formula tells us this equation. This is equal to 0 if d is even, 2 if d is odd. Okay. But we might say, okay, are there other equations other than Euler's equation satisfied by these numbers? And it turns out that there are. So there are several other relations. For example, let's say when the dimension is, I did dimension 6. So this equation says this. I guess I meant dimension 5. Confused now. Vertices minus edges. I guess it's just this. D is odd. It turns out that there's other relations that always have to be satisfied. For d equals 5, they look like this. So every simplicial polytope satisfies that. And every simplicial polytope satisfies this. So Euler's relation is just one of many relations. So what are these relations? We can describe them like this. So the F vector here is 6 vertices, 12 edges, and 8. For some reason I want to start with a 1. Here, one empty set, 6 vertices, 12 edges, 8 triangles. And now I'm going to define something called the H vector. And it's defined by the following thing. From I equals 0 to d. This is a very strange definition that will be clear in an example. So what I do is the following thing. I take my f vector and I make a polynomial out of it. So 1 times x minus 1 cubed plus 6 times x minus 1 squared plus 12 times x minus 1 plus 8. That's this side. Okay. I just take my coefficients And I just figured out what this polynomial is. Okay, so I did this ahead of time, and I found that you get this. And these guys are called the H vector. F vector, H vector. So you see each H number is kind of a combination of the F numbers, right? Each one of these numbers is obtained as a linear combination of the F's. And so here's a theorem due to Dehn-Somerville. For any simplicial polytope, we have that HI is equal to HT minus I. So this thing is always symmetric. It wasn't a coincidence. It's always symmetric. You should realize that this is a very strange thing because this guy has n degrees of freedom, right? Or d degrees of freedom, right? You have one number in each dimension. Whereas this guy, according to this theorem, only has half the number of degrees of freedom. Once you know the first half, you know the second half. So what that means is that even though vectors might look like they have d degrees of freedom, really they only have d over 2 degrees of freedom, and they satisfy d over 2 equations. And so this is why you get these extra equations over here. And in fact, f vectors of simplicial polytopes satisfy these relations and no others. And so these are all the relations. All linear relations. And this is motivated by the question, what if I give you an f vector? Or what if I give you a list of numbers? And I ask you, can you construct a polytope that is simplicial, that has this many points, this many edges, this many faces, and so on? And so there was this big question, which is, can you characterize all the f vectors of simplicial polytopes? And this is part of that question, right? It gives you a test. If you plug into here and you don't get a symmetric polytope, then that cannot come from a polytope. So these are these relations that actually come from. So we'll prove these next time, but this will do a sketch of the proof, so that you see that this is really a consequence of this thing being an Eulerian poset. Okay. But yeah, that's a good place to stop, and we will continue next time.